Hi, good morning, everyone. I'm Sigmod from Stanford University, and today I'm going to talk about our recent work on knowledge-based construction from richly formatted data, which mainly focused around our open source engine called Fonduer. This is a joint work with many great folks. So knowledge-based are everywhere today. So knowledge-based construction is the process of populating structured knowledge bases from unstructured information sources. In the past 10 years or so, a huge number of knowledge bases that have been built from both in the industry and academia. However, they have focused on either semi-structured format like DOM trees of web pages or unstructured text. There's a trove of valuable information hidden in richly formatted data, which I will define next. Our goal is to build a knowledge-based construction engine that targets on this richly formatted data. More and more information is expressed as richly formatted data, where semantics are not only expressed via textual cues, but also from structural, tabular, visual cues. To make this more concrete, here is a PDF datasheet from one of our collaborators working with hardware. People use different modalities to describe different information. In this datasheet, they use tables to summarize electrical characteristics, use list to highlight the key properties, or header to summarize the transistor type or transistor part number. So what's knowledge-based construction from richly formatted data? Let me walk through an example. Our collaborator wants to extract transistor information from this datasheet. Specifically, let's take a look at extracting maximum collector current from for each transistor part number from this datasheet. We invite you to think about how you are able to identify the maximum collector current number for these two parts here is 200. So now if you think of the pattern, like 200 is in the same row of collector current, the table is maximum rating table, or those letter number combination in the header are probably part numbers. You have already recognized what makes this data so challenging to handle. These signals you think of are readily apparent to humans, but not immediately accessible to computers. Let's take a deeper look. With richly formatted data, semantics are expressed in multiple modalities. Some knowledge-based constructions take an approach of simply filtering out those non-textual signals and instead interpret the document and unstructured text like this. Well, others try to manage the complexity of the task by limiting the context scope that is considered to just sentence or tables. In our experiment, we found that both approaches result in poor quality. In fact, if you neglect multi-model information, you can miss up to 97% of relations in these datasheets. However, manually extracting these signals is tedious and time-consuming. So how can we capture these signals from different modalities across a document? So there's a new and successful paradigm that obviates the need for manual feature creation, deep learning. So deep learning has started replacing traditional algorithms and beating human beings in many domains and tasks. It can beat a human being in reading comprehension, or recognizing images, or even in playing Go. So our question is, can we take advantage of this powerful tool and apply it to our problem? Of course, we'd love to use deep learning, but deep learning comes with a catch. We need a large amount of training data, and the traditional deep learning model are not optimized for handle multi-model signals. So in order to be successful, we need to address two questions. First, how do we gather enough labeled richly formatted data? Second, how do we model the characteristics of richly formatted data into deep learning model? So our answer to these questions is Fonduer, a weakly supervised deep learning framework for knowledge-based construction from richly formatted data. In the past 2 years, Fonduer has powered many high-quality knowledge bases. To have a few examples, Fonduer powers the DARPA MEMEX project, which is an effort to identify human trafficking crimes by extracting information posted on open and dark web. These knowledge bases are now being used by law enforcement agencies, and we are very proud of creating positive real-world impact. Our collaborators from Stanford Medical School has used Fonduer to create the world's largest gene-wise association study knowledge bases with good results, which is also very exciting for us. There are many examples in various other scientific domains and commercial enterprises. So machine learning-based framework, including Fonduer, requires several key components: input data, candidates, training data, and featureization and classification. However, what makes Fonduer unique is how each of these components are handled in the context of richly formatted data. Let's take a look how and why we generate training data and how we perform featureization and classification. So all machine learning approaches require training data. However, the breadth of signals in richly formatted data magnifies the need to have huge amount of training data. Obtaining this training data using manual annotations is time-consuming and expensive. Consequently, in Fonduer, we generate training data using weak supervision and allow users to deploy our framework in all sorts of domains. Let's take a look at an example. Suppose we have two candidates as shown on the document, SMBT with 100 and MMBT with 200. With traditional annotation, you'd need to hire someone to manually mark, okay, candidate 1 as false and candidate 2 as true. Even in these tiny data sheets, there are about 20 candidates. In the real data sheets, there could be thousands. So you can see how this could be tedious. Using weak supervision, we allow users to programmatically label candidates using labeling function, like the one showing below. This labeling function takes a candidate, like MMBT with 200 as input, and check if the current is in the same row of the keyword collector. As you can see, this is really just encoding simple human intuitions you use to identify the correct candidates in Python. Yes, something this simple is actually incredibly powerful, because in Fonduer, we allow users to provide weak supervision using multimodal information, like this table alignment information. Weak supervision in richly formatted data can come from a variety of sources or modalities, which make it much noisier than traditional supervised data. We use a data programming engine called Snorkel to systematically denoise these signals to generate probabilistic training labels. Snorkel does so by reasoning agreement and disagreement to learn the accuracies of these sources and allow us to easily create large training labels. If you want to learn more, Alex Renner will give a talk at tomorrow's STEAM workshop. You're welcome to attend. So remember how we said, okay, that simply allowing users to leverage multimodal information was incredibly powerful. When working with these translator datasheets, if we only rely on textual information to provide supervision, the quality was terrible. But allowing users to provide supervision, okay, by leveraging multimodal signals, the quality skyrockets. To better understand how people use weak supervision, we gather a group of non-domain experts and ask them to write labeling functions for these datasheets. We found that over 90% of weak supervision they provide relied on non-textual signals. In fact, with these datasheets, about 60% of supervision was based on the tabular information. In many domains, it could be nearly impossible to achieve high quality without a framework that preserves and exploits multimodal signals like Fonduer. Just like we augment the traditional weak supervision with multimodal signals to handle richly formatted data, Fonduer also enriched the factorization and the classification by augmenting the LCM model with multimodal features. Remember, deep learning has emerged as a front runner in many NLP tasks. One of the key drivers of this success is the use of long short-term memory neural net, short as LCM, a very effective recurrent neural net structure to handle sequential data. In richly formatted data, candidates are almost never located in the same sentence or the same table, and actually, in fact, can be separated by dozens of pages. So which makes LCM struggle to learn from these long-distance signals, like visual alignment or this document structure. So what do we do with these vital but long-distance signals? We go back to basics. By using multimodal information stored in the document, we can augment the LCM model with features from other modalities, such as structure feature, like this font and type information, or tabular feature, this header cell information. Effectively, we extend traditional LCM to go beyond the textual information and to include other modalities present in richly formatted data. This fusion allows us to leverage all benefits of deep learning model while also being able to capture the key signals from non-textual modalities. This approach also frees the user from needing to perform any feature engineering. So, do this multimodal feature matter? The answer is yes. With transistor datasheets, just removing tabular feature alone drops the F1 score by 14 points. In fact, in each of the domains we evaluate, the best quality was achieved when all multimodal features were present. Okay, let me walk through some empirical results and the real-world uses. We compare Fonduer with GeneWise catalog, one of the largest knowledge bases on GeneWise assertion study. We use the same set of documents. GeneWise catalog has been manually created by the domain expert in over past 10 years. Fonduer's KB took a CS PhD about 6 months. If we use catalog as a GeneWise catalog as a baseline, Fonduer were able to find actually 59% more data with high precision. Let's take a look at how people are using Fonduer in industry today. One of our collaborators at Alibaba has been using Fonduer to create knowledge bases that could be used to improve their search quality and user experience. Alibaba has an auction website which allows users to sell their things by writing descriptions in HTML. These descriptions can vary dramatically. Some are very simple paragraphs, while others are complex tables. Not only to organize their data, but also just for formatting their content. So Alibaba used Fonduer to extract the key fact like vehicles make and model from this massive data. Okay, to wrap up, Fonduer is our open source engine for building high-quality knowledge bases from richly formatted data. It allows users to leverage multimodal signals and also augment the deep learning model with features from other modalities to achieve high quality. Finally, it's being used today to support real-world applications. The new version is coming soon. Thank you.
Alibaba. So if the user can use the raw HTML to, I think they can also to extract the information, for example, using HTML, but when using the table.
Why using the table? Okay, the table is created by the user.
Yeah.
By the user, it's not like HTML. So there's no unified schema for that. You need to use some machine learning-based framework or some rule-based system to extract this information.
Yeah. But they can use the structure of the HTML?
Yes, they can use, but like the main content is basically designed by the user. So no unified schema for that.
So yeah, I have a question. So it's not clear to me how the if then else statement written by the user is then used by the model in order to learn the association that are done to train the system.
It's not for the weak supervision, you mean?
So, yeah, so from the supervised part, so there was a Python snippet there. There was, yeah.
Oh, this one?
Yes, this one.
Okay. So yeah, basically, user can provide like a lot of like labeling functions we call to provide a weak supervision, and they can cover like a subset of your data, and then we use this a huge amount of like labeling function, and use the label for the candidates to learn the accuracy for each labeling function. So okay, for example, this one, like okay, we have learn accuracy, and use this accuracy to predict the quality or the probabilistic of the candidates to be true or not with the probabilistic label.